Wow. He says it best, really. Welcome back to another stream today. As the title might imply, if you've seen that, we're going to be mostly working on some firmware today. But I have some packages to open, so I thought I'd start out with that. And Tuco is getting a head start on me. I think he's already managed to remove some of the packing material from that larger box without fully opening it. Hey, Tuco, don't eat those. I think I know what he wants in that large box. Hey, Tuke, is this the one you wanted? That's his favorite kind of cat food. Looks like there's something else in here, though. This is related to something else that we might be opening today. Hold on to this. Hey, Tuke. Well, cat gets his cat food. Hey, buddy, can I move these? Welcome back, everyone. So yeah, that first box, the one that Tuco was so eager to open, was mostly cat food. Although we also have these, you might have seen that it's a medical device of some sort. We'll take a closer look at this a little later. All right. Let's open this next big one. I think this one, yeah, so I've got a few things from Amazon, a few things from eBay, and then I've got one thing that a viewer sent in, which we'll take a look at. I think I'll actually want to set aside a whole stream just for like actually digging into that one. I know what it is because I've got an email related to it, but we can pretend it's a surprise and just open it here. So my plan is to open that on this stream, but maybe save some time later for actually digging into it. Hey, Tuco, you've got a bolt. Oh, this doesn't even have... Whoa. Yeah, Tuco, I just made a mess. Oh, what a mess. You really need to get that automated bolt thrower happening. Tuco is very addicted to his games, and it's occasionally gets hard to get work done because Tuco is just always wanting me to throw the bolt. Distracted for another little while. Okay, so this long one, I have a pretty good idea of what's in here, but let's just give it an open. I think I need an actual knife for this. Do I have an actual knife? Oh, this is going to be the worst package opening knife. box is mostly empty. Yeah. Carbon fiber rods. This is a large box for these rods. So, got these for Tuco Flyer. Let's actually maybe take a look at these on camera. So these, I think, were, if I'm remembering right, oh, they're even labeled. Yeah, 8mm outer diameter. I think it's a 6mm inner diameter and 1/2 meter long. So the basic idea for this is this would kind of hang down and provide, it provides some vertical support, but also stiffness for holding the camera at the bottom. And then it would be anchored at the top by kind of a little saucer-shaped platform that attaches to the nylon cords that go off to the winches. So the reason carbon fiber might be nice for this is that, I want something stiffer than plastic and lighter than aluminum, and these rods are pretty widely available because you make hobby quadcopters out of them. Oh, and geez, Tuco's going. You might see him on the camera in just a sec. Tuco. He's gonna make sure that box is empty. Oh, maybe we don't want to be servo AF today. That's pretty nice. So that's pretty good. These are nice and stiff and very light, which is pretty much exactly what I wanted. So I don't know if I'll need both of these. They just came in a 2-pack. I'm thinking just one of these with the gimbal hanging at the bottom, maybe some electronics mounted along the middle, and then the support near the top. And the idea behind wanting it so long is that actually being able to have the camera kind of reach down into the workspace here while having the nylon cord stay a little bit more above overhead seems like a pretty useful thing. So that's nice. Let's keep these somewhere safe. I don't think I'll be doing anything with these right now, but it's good to have them, and as soon as I actually do a little bit more CAD modeling, I can start to 3D print stuff that will attach to these. So that's really great. Jarrett says, will that cause issues with wobbling? Yeah, the bot will tend to act like a pendulum with, some amount of mass kind of at the bottom and then like a long arm. That will actually tend to stabilize the camera somewhat, but I'll have to be careful with my acceleration so that I don't tend to, start the camera oscillating. If I didn't have the 3-axis gimbal, then I would definitely be worried about that, but with the gimbal, I'm not so worried about it. I think it'll just mean that that I need to be careful with my acceleration, which was probably going to be the case anyway. But we'll see. Oh, Tuco. Looks like I've got 2 more Amazon packages and a couple more China packages, and then the package that one of you sent in. Oh, and this one, which I don't recognize. This one's really little. Let's open this one. I think this was something that came in via Amazon. Oh, delightful. These are some of my parts for the potential hacking around on the NTSC device that we had earlier. These are just PLC-C sockets. I think these were pretty inexpensive, and these are the kind that have a surface mount footprint, so I think I can just solder those onto the existing boards after hot airing off the ROM chips, and then have socketed replacements if I want. That'll be nice. I don't understand. I'm just going to ignore all of Robert's totally random criticism about stuff that doesn't matter. In this case, the Ethernet cables are orange because they're color-coded for the robot. Oh, ha ha ha! I got a fidget spinner. This one seems to have all sorts of burrs all over the bearings, so maybe you get what you pay for. I 3D printed one, and it was pretty good, and I thought I'd actually get one. So, no one wants to see that. What's next? Oh, relatedly, more bearings. Because I only had 606 bearings, I needed some 608s also, so just bearings. Oops. Not much to see there either. All right. I think next is, so I've got one marked electronic parts, and I think I might have, oh, they're both marked electronic parts. Let's open the lighter one first. Oh, I think Alistair was asking if the fidget spinner was for fun or for hacking. I think that was just for fun. I 3D printed, there was one on I think it was on Pedro and Ruiz's show on Adafruit. They just did like a quick video on this one that had print-in-place plastic bearings. And I was like, oh, I don't have any of the right size bearings to make any of the usual fidget spinner models, but I could just throw this one on my printer, and so I did, and then it was fun. It was fun, so I wanted one that had better bearings. What do we got? So these appear to be some circuit boards with little headers. Oh, these are IMUs. Well, great. So I had been designing the firmware for this flyer around the Bosch BNO 055 IMU, because I had one of those handy, but I figured I'd also pick up some of these other breakouts since they're inexpensive. I think this is the MPU 9250. I think these are just a bunch of those. Yeah, 9250. It's just a different IMU to choose from for some of these projects, and also because I only had one of those Bosch sensors. But that might be relevant a little bit to this stream, because actually the first thing on the list of actual things to do on this stream was probably going to be to debug the driver I'd started writing for that thing, for the Bosch IMU. Alright, so that was the tiny package. The less tiny package. What is this one? Ooh. Yay! This is the one I've been waiting for a while. These are analog distance sensors. Oh, and it goes on the rack. Yeah, analog distance sensors. So these things, they're pretty classic, like robot obstacle avoidance sensors. So these are made by Sharp. As far as I know, they're like official Sharp sensors. They aren't like cheap clones or anything. They're just usually a little on the expensive side. Like if you buy these new, they're like $6 to $15 depending on where you get them from, I think. But I found an eBay lot of them for just a couple bucks each. And since I wanted like 8 of them for this robot, it was worth waiting for the slow shipping to get some of these. But these are kind of interesting sensors. The way they work is actually by using some interestingly shaped optics here to measure. I think they're actually measuring something like the size of the dot instead of the intensity, so that they can measure distance while mostly correcting for the actual reflectivity of the object. So the upshot is they give you an analog signal that's proportional to distance roughly, and so I have like 8 analog inputs set aside for these on my firmware. So now that I actually have these, we can test them to see how well they match what I've been reading online and what I have in my CAD model as far as, the distances they're sensitive in, and I can check to see if there's any interference with sensors that are nearby or between these and the LiDAR sensors I'm using. So I got a bunch of these. I think I got like 15 of them or something because they were nice and cheap. Yeah. Do I have a box to put these in? Now, all these sensors work by sending out IR light and then measuring the reflections. And there's a decent amount of sunlight in here, but I've been testing these sensors, or at least the LiDAR ones, during the day, and they seem fine, and they're the ones that are actually operating at a long distance. So I think they have a powerful enough laser in them. So I'm going to put most of these aside, but let's at least get one of them hooked up soon. I'm going to finish opening mail, but this is one of the next things we're working on, so I'll just leave this out. Okay, cute. I think we are down to the package that one of you sent in. Alright. This one seems complicated. I actually do know some about what's in here because I got an email in it ahead of time, but that part is totally optional, and I'm just going to open it so that you can enjoy some of the surprise, if I can remember which of these. Alright, so this comes from Bealsburg, Pennsylvania, from D. Ferguson. So thank you very much. Always appreciate hard work to dig into. And it sounds kind of complicated, like there are a lot of kind of parts rattling around in there. Let's actually cut that tape instead of just mashing it. Yeah. So go to box. RS Medical. Yeah. So that's the whole thing, actually. There's, some bits of plastic in here. All right. Opens on this side. Oh, that's great. And there's a note. Oh, that's really great. Aw. So this comes from Dory, who says, "Hi, I included some knit mice for Tuco along with the hardware." Oh, and that's really great. And they made it from wool and, yeah, polyfill stuffing. Oh, that's so cute. Little handmade mice. Oh, these look like something Tuco would be really into, especially the tails. Aw. Squeak, squeak. Hey, Tuke. Hey, Tuco. What about this? What do you think, Tuco? It looks like a mouse, but it's made from wool. Oh yeah, I think he's gonna be into this. Aww. You just want to hold on to that, Tuke? Oh, I was looking at the monitor and I didn't see where that went. Oh, Tuco, here it is. Well, I'm sure Tuco and I are going to have hours of fun with these little guys. Thanks so much. Aww. Oh, that's so good. Tuco just likes interesting textures. I didn't smell any catnip. I wonder if they have. No, it just smells like wool. I don't know. I think he likes the texture. Oh, that's so good. Well, I'm going to keep the other mouse over here, since I think Tuco has only enough attention for one mouse at a time. He just wants to put the whole thing in his mouth. Oh, Tuco, are you... Am I gonna find mice in the rack now? Hey, Tuke. Aw. Well, that's really great. Oh man, I just can't get over how good this is. I just noticed on the other side of the note, it's actually a postcard of a bear. It's like a woodcut drawing. Oh, I could just watch Tuco all day. I mean, sometimes I really want to get work done. You want that back, Tuke? Oh no, the YouTube copyright bot. He's gonna flag the tea kettle song in this video now. Can't get the right angle here. If only we had a robot that could move the camera around. They can stare each other down. Oh man, I could seriously just have a 5-hour stream just of Tuco, but maybe I should get on with things a little. So, as I said, I don't want to go into a huge amount of detail in this right now because I think I could easily turn this into a separate stream, so I think we should probably do that. But this is a TENS device, or a TEMS device. It's a muscle stimulation device that uses electricity. And so this was being used to treat fibromyalgia, and I think the story behind it is that it was working fine and then just all of a sudden stopped, and so we're not really sure whether it's, you know, some kind of, like a self-test failed and there's like a lockout that happened, or whether it was just a flat-out electrical failure or something. But it's an interesting little piece of hardware, and there's something wrong with it, and so we could take it apart and try to figure out what's going on in there. So a little bit of user interface, some of these connectors. And so this does not come with any of the actual electrodes that contact the skin, but in case we get to the point of needing those, that's why I picked up a pack of those. These are pretty cheap and standardized, so I got a few of those to experiment with. So, well, thank you so much, Dory. This will be a nice piece of hardware to experiment with on an upcoming stream. I think for the moment I'm going to put this aside and we can work on some firmware since I had some of that queued up this morning. But thank you so much. Really appreciate the both the cat toys and the hardware. That's really nice. Hey Tuco, where'd you put your mouse? Are you looking for it already? I don't see where you just... I'm sure I'm going to be looking for this mouse a lot now. Oh, there it is. Hey, Tuke. Hey, Tuke. No? All right. Oh, B is asking if that mesh sleeve was metal. I think if you were talking about the one around the cables that came with the TENS device, yeah, I think that was just plastic. And this sleeving that I've got around the cables, that's all just like split loom tubing. Tuco circling the cat food. All right. Well, I think that ends my little mailbag segment on this particular stream. I think the next thing I wanted to do was just give a little bit of a tour of some of the firmware stuff I've been doing, and then maybe I can pick up on that and work on it until one of us gets frustrated. So, welcome back to the desk. So, you might notice I've got some sensors. Let's also get the camera back here. Crotch cam. All right. So for a little bit of background here, I'm trying not to get too deep into this, but working on this cat-following robot that contains many parts, some kind of earthbound winches in the corner of the room, and then this flying thing that has a bunch of sensors and a camera gimbal. And the architecture I decided on was to connect them all with Ethernet. Basically, each of the kind of peripheral robots that doesn't do much except kind of manage its own local sensors and motors or whatever. Those devices will all connect back to a central controller over Ethernet. And that central controller can just be any old computer. I think in this case it's going to be the same one that does the video streaming because that'll make it simpler to integrate the computer vision. But basically, this is going to act like a control network for the robots. So kind of like RS-485 or some other, lower level network, but in this case I can just use standard 100 base T switches and cabling. So, these microcontrollers were pretty handy. These are the, oh man, the model number for these is super weird. So TI calls this series of microcontroller the Tiva-C, and this is one of their connected launchpad development boards. The upshot of this is it's a $20 on DigiKey microcontroller board that includes Ethernet and a bunch of peripherals. So I've been using that to interface all the hardware I want to the network. And then the architecture I've been using for that is, hey Tuco. I think I hear a bolt, like you wanted to play with one. All right. So then I've been basing the software architecture for this off of this open source project. Well, it's on GitHub. The licensing on it is a little bit weird because it's basically just a collection of TI's like dev kit code that's been modified to work with like plain old command line GCC build tools. So bot firmware is the stuff I've been working on, and then GitHub. Yeah. So this Tiva-C project is what I've been... Oh, did the video grabber die again? It's back. Okay. So I've been basing the firmware off of this GitHub repo, which is basically just a collection of TI code that's been massaged into a format where it's easier to use with kind of an open source support system rather than their IDE. So you can build with GCC, you can upload using this little open source LM4 Flash tool. All the code is pretty much the same, it's just in a format that I like a little bit better. So this driver lib is TI's driver abstraction. And this stuff is all licensed in kind of a weird way where it's like almost open source, but it has some weird clauses in here that make it like not actually open source. because you can only use it on TI hardware, or at least some of these are. This one actually looks like kind of BSD plus advertising clause, but other files in here, like for example, all the examples here include just like copy and paste code that includes a license that says this is only for use on TI microcontrollers. And this thing, which I've complained about before, I just find this to be like, I can't imagine a lawyer actually being able to explain how this is enforceable. Like, viral in quotes is not a legal term. So I don't know. So some of this is just stuff that that's in TI's repository that I reference from mine, so I didn't bother changing it. But then some of it is actually stuff that I would have had to like copy and paste, like that startup file. So in that case, like I didn't want to like use some dubiously licensed stuff as the starting point for something I was then going to be adding to. So instead, I just chose to start over on those files. So what I ended up with is this repository, this tucoflyer/bot firmware. And so it's a single repo that builds firmware for all the bots. All the bots run the same firmware binary. They're just configured differently using the EEPROM. And so you can see this references that Tiva-C repository, has a plain old makefile that just builds stuff. And all of this stuff in source is open source code that I wrote for this project, or stuff that like wasn't licensed and I could just copy over from like linker script. Or like that startup file, I replaced it entirely with my own. And so this has all the interrupt vectors I need. This actually just calls memcopy and memset instead of re-implementing that. Oh yeah, so I'm getting a little scattered here because there's so much to talk about. Hey Tuco. He's scratching at the door. Yeah. Is any of this interesting? I feel like I've been avoiding streaming about this firmware stuff because like I find it so boring that it's hard to get other people excited about it a lot of the time. All I'm really doing is building a really simple interrupt-driven firmware around TI's lwIP wrapper. So this is calling into TI's wrapper around the lwIP networking stack, which handles actually gluing it to their Ethernet peripheral. And there's a decent amount of complexity in there, but I've been able to disable most of it, so it's basically just handling ARP and UDP and ICMP at this point. So it's a super, super minimal networking stack with only a little bit of dynamic memory allocation from pools. It's, pretty inoffensive for this kind of application. And it's a single-threaded networking stack, but the way TI handled this in their existing wrapper, which I've continued in this application, is to just run the entire thing in the context of the network ISR, which has some weird implications. It means that if you're handling activity, if you need to transmit something just asynchronously, not due to receiving something, then you have to synthesize a network ISR to kind of get yourself back into that context. There are other options, like you could have disabled that ISR and then called into it from the main thread, but then that causes other problems. So this was TI's solution. And so once you're actually in effectively the main loop, so this settings console here is effectively the main loop of the application. And this becomes the lowest priority task. So when nothing else is going on, it's just sitting there looking for serial port input and handling a little command line that you can use to adjust the EEPROM settings. So that settings console is just a busy loop, or just a loop that hangs out forever answering serial port commands. But while that's going on, you have interrupts doing everything else. So all the network activity is serviced by this lwIP interrupt. And then periodically we have network-related timers that are fired off by the systic interrupt, but instead of calling directly into the network stack, this actually just updates a global timer and then sets a flag that asynchronously enters the lwIP interrupt. Likewise, if we get data in from the gimbal, so the gimbal is just attached via a UART. When we receive, so here's the UART IRQ for the gimbal. So it actually just stores incoming data on in a ring buffer, and then if we need to transmit a packet, so if it's detected the end of a gimbal packet or the buffer is about to be full or whatever, then it actually just sets this flag to manually trigger an Ethernet IRQ, in which case we'll end up back here on the lwIP context and we can send a packet. So it requires a little bit of attention to detail in terms of like which interrupt context something's running in to avoid stomping on anybody's concurrency assumptions. But it's pretty simple overall. So in this main, this is the main functions of the firmware. We're just conditionally initializing different bits of hardware depending on how this particular bot is configured. So for example, the flyer has a gimbal and some LEDs and some sensors, and the winch just has a winch and some LEDs, and not these sensors, but just the sensors that are built into this winch object. So I've been trying to keep this pretty modular so I can just add stuff to it. And then the individual sensors mostly just work by initializing some asynchronous thing that usually involves some hardware peripherals and their own interrupt handlers. So for example, this X-band sensor, this is a 10 gigahertz, basically a Doppler radar that detects humans or animals being nearby. And it seemed like a kind of useful input to have, and I had one of these sensors kicking around. And so it just produces pulses at a rate proportional to how fast objects nearby are moving. So in that sensor, for the initialization, I'm actually just setting up a timer. The timer peripherals on this micro are really nice. They're really flexible. I'm using half of this timer as a pulse counter and half of it as an interval timer. And so every time the interval rolls over, which in this case is 100 times a second, I just look at how many pulses have happened and then filter that result with a low-pass filter. And so all that happens from this timer IRQ, or from this periodic poll that happens right before we send out a packet. Anyway, the upshot of all that is that when we load this firmware, we get a bunch of sensor readings coming back in these UDP packets every 250th of a second. Let's just rebuild the firmware just to have that on the recording. So I got a bunch of these modules. Oh, right, I was in the middle of adding DMA support, so it doesn't actually compile right now. That's fine. Let's just use the firmware that's on there. So yeah, so anytime the firmware is running, it'll just be spamming out packets out on UDP port 9024. So we can just pick those up even just by listening with TCP dump. But it's a little bit more convenient to actually decode them with Python. So I've got a tiny little Python script here that just opens a socket, receives UDP frames, and looks for one particular known packet type, which are the sensors I'm working on right now, and just decodes a bunch of integers. So you can start to see what we've got so far. There's the protocol definition. So the protocol is really simple. I wanted to keep it really stateless, so I wouldn't have to worry about like connecting to the bots and disconnecting to them. I wouldn't have to, I wouldn't have to have any delays that get introduced because of that. I wanted to keep it pretty easy to keep all the bots really tightly synchronized, like within 10 milliseconds or so, and if they get out of sync for any reason, to just like stop the entire system. So it's all just based on spams of UDP packets going out. And each UDP packet has a 1-byte header, so there's like a loopback protocol, but all the rest of these, so you can send packets directly to the gimbal serial port, and likewise when packets come back from the gimbal, this only knows enough about the gimbal protocol to find the ends of packets, and then it just wraps them in UDP and sends them back over the network. It has these sensor packets, which are just this structure with a little header. So this structure is what we're seeing right now. So it starts out with X-band, then LiDAR, analog, and then IMU. So these first three numbers are the X-band sensor. Let's take a look at that on the O-scope. Oh, roll mode is not helpful there, is it? Oh, it kind of is. Okay, that's the output from this little X-band motion sensor. This is the one sold by Parallax. It's become a bit of a commodity item. Like, you can find a lot of different models of these now. That front board is a radio transmitter receiver at around 10 gigahertz. The back board is a signal conditioning board. And so there's a little trim pot on the back you can use to adjust sensitivity. That basically adjusts the threshold that it uses to detect one of these pulse edges. There's a correlation between motion speed and the pulse rate that you see. Let's see if I can get that in the frame. It doesn't really detect that well so close, though. So, it gives you some idea of how the sensor works. So the way I'm processing this is I'm actually just counting every positive and negative edge that happens within each 100 millisecond period. So this first column is just a raw count of how many edges happen. And so that updates every time we send out a UDP packet. So even between those 100 millisecond periods, that'll just update right away. And so that's good for if we just want to detect any activity right away, we could look at that number. The second number is averaged. Basically, it's a infinite impulse response low pass filter that just averages out the differences in this first number over every 100 millisecond interval. And so you can see that it's roughly proportional to how much motion is happening. So here there's like a decent amount of motion. If I were to just kind of sit still, then that number would drop. If I were to just move a little bit, then that number would kind of stabilize at a lower value. So that I expect to be more useful for like adjusting the lighting on the robot or maybe behavioral decisions. And then that third number is just a counter that increments every time we have one of those 100 millisecond periods. So if we just look at individual values, you can see that these are on different clocks. The UDP packets go out at a 250 hertz clock, and this measurement happens at a 100 hertz clock. So some of these are duplicates, and having the counter in the packet lets the receiving software know which ones are duplicates. So then the next numbers have to do with the LiDAR. So we have 4 ranges and 4 counters. So this next number, the one that's in like the 140,000s right now, that should be the LiDAR range for the sensor on the gimbal. Yeah, let's put that one on the O-scope. Not that one. That one. So this signal is at a very different time scale, you can see. So this signal is encoded as a pulse width. So you can see, let's get a little closer. So in trying to digitize this, I needed to know what the minimum and maximum pulse widths would be. I needed to know how much resolution I would need. The datasheet, excuse me, the datasheet actually was claiming that this had like a 10 microsecond step size, which seemed kind of enormous. But from looking at this on the scope, I couldn't find any really noticeable step size. So, okay, so I'm triggering on the positive edge. The trigger is pretty stable. And then let's go to the end of this waveform. So already you can see it's jumping around a lot, which would suggest that if I were to average this in software, I would maybe get a slightly more accurate reading if that's what I wanted. But if we try to zoom into this, I'm looking for quantization. Let's turn on persistence. And that doesn't look like a 10 millisecond quantization to me. You know, I don't think that's all just triggering error. I think you're seeing a PWM output with maybe not a lot of repeatability, maybe not a lot of precision, but it does seem to have a lot of different values that it can output. So it does not seem to be quantized, which tells me that any timer resolution that I can throw at this might help, which was originally starting to seem a little bit daunting, given that I thought I had a 16-bit timer to work with. But actually it turns out that when you put this chip's capture timer, or put its timers in capture mode, they all become 24-bit. So having 24-bit cycle counts that are all clocked at 120 megahertz actually turn this into quite a nice timer for these. So these numbers, I'm just getting 2 interrupts for every pulse, one at the rising edge, one at the falling edge, and then I'm just subtracting them. So it's a little hard to see this accurately because we're still jumping around so much, but this column, the fourth one, is corresponding to the sensor we have on the scope right now. That was a hiccup in the Raspberry Pi. And then correspondingly, this is the counter that just increments every time that one gets a new result. And so we can see also the LiDAR sensor doesn't update as fast as these UDP packets are going out. UDP packets are 250 hertz, and the LiDAR sensor updates at maybe 60 hertz or so. So you can see this increments in kind of a sporadic fashion every time there's a new measurement. And likewise, this is also another LiDAR channel. This is the one that's pointing straight up on the table here. So yeah, that's the other LiDAR channel. And so I've tested all 4 of these. They're all implemented slightly differently in software because the pins are all over the place, but same technique. The driver for that is really simple. So just setting up GPIOs and pin mappings. And we're using both timer 3 and timer 5. And each timer can time 2 channels of LiDAR. And then each one has a separate interrupt. And these are kind of copy-paste, just with different values. So it could be a lookup table, but this seemed more straightforward. So each one gets the corresponding timer value and then looks at the state of the pin. And so this is relying on having a minimum width of the pulse, because we need to be able to get an interrupt in there to record that positive timestamp and then get another interrupt in there on the negative going timestamp. But the minimum length of these pulses are pretty wide, so this is no problem at all. And so it just records the rising edge, and then when the falling edge happens, it actually updates that buffer that we're sending out via UDP. Robert is saying that low-pass filter seems to have a huge lag time. Well, yeah, that's the point. It's a very low-frequency filter. This data is so slow that, like, to get a meaningful amount of precision out of these really, really slow counts, I need a filter that takes a while to settle on a value. Like, there are ways around that, but I mean, there are more complicated filters that have other trade-offs, but in this case, I don't think any of those would be applicable. Also, I don't really care that much. Okay, so I think that's all I'm going to talk about with the LiDAR right now. The next numbers here are the analog inputs. So those are even simpler, especially thanks to this bit of hardware where you can literally just tell the hardware to sample a list of A to D channels, and then it just does that and gives you a DMA buffer full of results. So that seems pretty handy. Every time one of these IRQs happens, we just retrieve a bunch of completed analog samples. That's the entire A to D driver. So let's take a look at this IR distance sensor maybe. And then this next part over here, that's where the IMU data is going, the end of the packet. And this is all zeros because I haven't gotten the IMU driver working yet. That's also to be done. Okay, let's get the data sheet for these sensors. Oh, is my keyboard no longer working? Thanks, keyboard. Alright, these are the sensors we're about to try out. They run on 5 volts, and the output also goes to 5 volts, so I might need to divide it. Let's take a look at that. Looks like the color code's pretty sensible. So yellow is V out, black is ground, red is VCC. Alright, let's put this LiDAR aside and try to sneak another sensor in here. Oh wow, these wires have the tiniest tin section. Not really light on the power consumption, they're like 30 milliamps. Got some interesting modulation on there. Is that mine or is it the sensors? Oh, maybe I don't need to put this into a voltage divider. My A to D is going to give me a range from 0 to 3.3 volts, I think. But this looks like it tops out around 3 volts anyway. Is that power supply noise? That's my power supply. It's a little noisy, but that's not explaining this. That's fine. Well, let's just try plugging this into the A to D and see how well that works. What's that? All right, proximity sensor 0, PE3. PE3. That doesn't seem right. PE3. Oh, it would help if I put this on the right connector. Ah. So now we're looking at this column of numbers. The one that's in the teens with some spikes now. That seems about right. It's going to get a little hard to tell if these sensors are giving me the readings I want without making a mount that holds them all at the right angles. But that's looking promising. It's possible that a capacitor on there might help. But I don't know. It's probably fine either way. So what if I have two of these? Will they interfere with each other easily? I'm curious how folks are for like interest in banging head against I2C drivers in real time. As I said, I've been doing a lot of the firmware stuff kind of off camera because it's like not even quite exciting enough that I think I can get myself excited about it. But I'm curious if other people think that's accurate. I think my intuition was that maybe I should do an occasional stream with like a little bit of firmware status, but then do a lot of the work off camera, since I think when I'm editing I would just end up cutting out a lot of that stuff anyway. PE2. Let's unwrap a second sharp sensor. I think I probably will do a really simple PCB or something, just as like a power breakout / signal wire management kind of board. It's totally not necessary, and I'm not really sure yet, but I can see it helping, and it might also just help me document the wiring a little better. And it's so easy for me to make PCBs here that I might as well. Ow! I was plugging something into a header, and I had a different finger positioned such that the force of plugging it in caused a header to go into that fingernail. Not that hard, I guess, but hard enough to be annoying. Let's maybe use some double stick tape to put these down next to each other. One sharp sensor. And in the actual robot, these would all be angled outward slightly. Right now, I'm just going to try sticking them on the table kind of flat. So I've got 2 of the sharp sensors and 1 of the lidars pretty close to each other. Let's see if I can get anything good out of these. Okay, so the 3 sensors, we have, there's this column, yeah, this is the LiDAR column, which seems fine. It's only detecting when I'm over the LiDAR. And then these first 2 that are bouncing around are the first 2 analog channels. So there I'm hitting only the second sensor, and there I'm hitting both, and there I'm hitting only the first. There are some states where the distance reading is pretty wrong. Like I thought I saw it going up to like 2,000. This would be really nice to have some graphing at this point. I also, I guess, have some decisions to make as far as like what the framework I'm using on the controller side is going to look like. I mean, the stuff I've been putting together on the firmware side is, you know, stuff that I haven't spent a huge amount of time on, but I at least intend it to be somewhat long-lived, like stuff that I hope will work out for a while, whereas all of this stuff is super temporary, and I don't really know what I'm going to be writing the bot controller in, or mainly the constraint is it is probably going to be running on Windows, maybe Linux, but I'm probably putting this on the streaming machine, which is already running Windows. It can pretty much run on anything that has networking and a video capture card. But the actual video parts are probably going to be in the form of an OBS plugin, because I need that to have access to the raw, low-latency video stream. But then the rest of the bot can and probably should be outside that OBS plugin, and it could be written in some other language, like the OBS plugin probably has to be written in C or C++ or whatever. But the controller proper could probably be a separate thing written in Python. I could also probably learn another language like Go or Rust and use that. Yeah, I think I'm getting a decent amount of separation between these two sensors. Anyway, I'm not worried about that. The actual way these will be used is placed kind of more like this. Could make this into a line following robot or something. A bump following robot, a hill following robot. So the rest of this packet, let's turn off some of this. All of that's just set aside for the IMU. And the IMU, this again has some reasonably high-level library stuff to build on top of. I'm using this I2C master implementation in TI's sensor lib here. And that's basically just an interrupt-driven state machine that handles all the phases of I2C master transactions, and you can give it a queue of transfers. So every time we're about to send out a network packet, this initiates some I2C activity, which is either finishing the setup process or issuing an actual read for IMU data. And when the read comes back, we just increment a counter. This has not been working so far. And I wrote this last night without the oscope hooked up or anything, so I haven't really tested it properly. And I think right now the firmware doesn't even actually compile, because I was also adding some DMA stuff for the LED output. Yeah. I was starting to fill in a DMA-based little SPI LED driver thing, but I was still reading the UDMA documents. That warning bothers me a little bit, but not enough to go and fork that repository to fix it. Okay, so I can flash this 2-coflower bin. Let's also get the serial port handy. Had a little bit of trouble with the serial port. It seems like maybe the serial port peripheral in the onboard debug micro is not especially well implemented, or maybe I just keep hitting OS-specific bugs, but it really had problems with this serial port on macOS, and on Linux it seems to mostly work, but still occasionally confuses the serial driver. Should just really not have a password for this Pi. It's not helping. Yeah, anyway, so if we start the firmware fresh, we can see it gives a little message, and then just periodically gives us stats about what IP it's on and how many packets it's receiving and transmitting. And if we press enter, we can break out of that and get a little shell where we can show the EEPROM status. There's a few other commands. Mostly I just used this so that I could do the initial setup for the robots, but it also might be helpful for debugging or tuning. So we have a little bit field that tells it what features this bot has, and then some debug flags. Oops, debug flags. And then this is the UDP port, and then IP address for the central controller, current IP address for yourself, netmask, and gateway. So if I reflash this, all that EEPROM stuff sticks around and I don't have to reprogram it. Flashing, and then we start. So yeah, I need to work on this. I need to fix the IMU input. Oh, while I'm showing off stuff that works though, the gimbal works. So we have a little gimbal driver. You can send it packets. You can pull for incoming packets. It can also asynchronously flush packets out when it detects the end of a gimbal packet. So for the most part, this is just like, this doesn't know much about the gimbal protocol. It's just shoving bytes from UDP to serial and back. But in order to deal with that impedance mismatch between a byte-oriented protocol and a packet-oriented protocol, to efficiently make round trips back and forth between the controller and the gimbal, we have to have this flush out a UDP packet with the received gimbal packets as soon as that packet's actually ended. And to do that, it has to be able to detect the end of a packet. So there's a very simple state machine here that just knows how to detect the two packet formats we know about. It doesn't actually calculate CRCs or any of that. It just looks for the end of the packet. And when it either detects the end of the packet or the buffer's more than half full, then it marks the UDP, or marks the buffer as needing to be flushed out over UDP. And we'll try to do that immediately by raising the interrupt. So in addition to the telemetry here, so in that bot controller package, I've also got some copy and pasted, hacked up copies of bits of the Fayutech gimbal stuff that I'd been working on in Python earlier. So this is the exact same FYProto module, but instead of the serial port-based gimbal interface, I had this new Flyer gimbal file, which is largely the same, except instead of serial port, this uses UDP datagrams. So outgoing packets all get wrapped in UDP, and incoming packets get taken apart the same way. So we can do gimbal param diff, and just like before, we can get all the gimbal parameters and watch them move around if we want. Can run the controller. And then, so now this is actually running over the network. The Xbox joystick receiver is plugged into the Raspberry Pi, which is then running this Python script and communicating to the actual gimbal over UDP packets. So this is pretty close to being able to just plug in some computer vision and have this track targets in the video, which I'm pretty excited about. And this is also compatible with the same HTML UI that we've been using earlier. Oh, in fact, I don't have a copy of it in this project, but literally if you go to the FY Gimbal project, I can just run the same UI. So I'm pretty happy with how that's working out. If we take a look at the network traffic, yeah, if we just go back here and dump only port 2034 or 9024. So now we can see two different kinds of packets coming back. So this one, where's the first actual payload byte? I think this is the first payload byte. So this is packet type 2, which would be all the sensors from the flyer. And that just spams out 250 times a second. And then this is a response from the gimbal. So after the O1, this is just going to be data from the serial port. And it tries to split this right at the end of the packet. So we've got the packet header, then right there, that's the end of the packet, the checksum. And you can turn off the motors. All right, anything else interesting? I think that concludes the interesting part of this. I think I've mostly just got boring debugging to do. Oh, a question from Peter in chat who asks, how many updates per second do you get? Are you talking about the gimbal? With the gimbal, it's going to be limited by the speed of the serial protocol. So the gimbal right now, I'm talking to the gimbal over a 115K serial port, which is the bottleneck. But I could increase the speed of that serial port by patching the firmware further, but I don't think I need to because I mean, it's a little bit of a bottleneck if I'm trying to like slurp down all of the parameters from the gimbal. So this gimbal param_diff script, this is a little slow because this is waiting on the serial port. But if you're pulling only the things you're interested in, it's plenty fast enough, and I haven't had to worry about the serial port. In practice, the update rate of the gimbal parameters, that hasn't really been something I've had to worry about because the gimbal motion is so smoothed anyway that as long as I'm updating it at more than like 30 hertz or something, it's not going to be noticeable, and it's probably more like, you know, over 100 at this point. As far as the graphs, I haven't been measuring what the update rate of those graphs are because they just use all the bandwidth I have and run round robin. So the bandwidth is just split evenly amongst the graphs. And at the Ethernet side, all of that has just been really nice and fast because the Ethernet link is 100 base T, and it's all done in hardware with DMA, so I can just send back those telemetry packets pretty much as I want. And I haven't tried pushing it much faster. 250 hertz seemed like plenty given the resolution of the sensors I'm working with. Because I think the fastest sensors might be like I mean, I can sample the IR sensors as often as I want, but I think in practice, the fastest sensors that are actually going to be giving me data at a rate close to their sampling rate that's actually meaningful are maybe the IMU, and I think that's mostly 100 hertz. So my goal with the 250 hertz UDP packets was to mostly just solidly oversample everything. All right, well, what about the IMU? Where are we at there? So we're getting these poles, I assume. Yeah. So every time, so this lwIP host timer handler, I've set this up to happen at this bot tick hertz, which is 250 hertz. And this just handles everything that's periodic that has to happen with the lwIP, effectively with the lwIP lock held. What's actually happening is this is running on the Ethernet ISR. But if you're thinking about this in terms of normal operating system concepts, it's like we have a networking mutex held when this is called. So, and this is actually sending out packets. So I could add some serial debugging to ensure that we're actually getting there, but I don't think that's necessary. So we're initializing I2C. I think I'm just going to hook the scope up and see if we're actually getting any packets out. So we need the scope. And I'm excited to just make a 3D printed thing that holds a whole bunch of IR sensors now and see what the aggregate of all that gives me. I'm planning on having 8 of those sharp IR kind of close range sensors in a ring angled outward just slightly to basically put kind of a truncated cone of protection around the gimbal so I'll know if something's about to bump into it. And then the LiDARs are going to be used more for determining the overall height of the bot, and the multiple LiDARs is really just so that it can handle some occlusion. Well, the LiDAR on the gimbal has a more specific focus, but the 3 LiDARs pointing downward all do pretty much the same thing. And it's a bit overkill having 3 LiDARs for that, but that's what I had, and it seemed like a good number. Okay, green channel. Let's make that SDA. Grounds. How were there ever enough grounds? Oh, we've got some packets going out. We are trying to talk to this thing. Why do those look so fuzzy? Oh, is there an insufficient pull-up situation going on? I thought we already had pull-ups, but maybe that's clearly not the case. Are there software pull-ups we can enable for this? Oh, GPIOs. Oh, that's interesting. I just poked reset on the board and my I2C traffic went away and didn't come back. Which could also be due to the pull-ups being missing, but it's just interesting. Oh, these are weak pull-ups. I probably want an actual external, like 4.7K or something. Some soldering. This is getting a bit messy. Aww. Oh yeah, there's a question from Peter about I2C and if it's going to be fast enough for this. I think it'll be fine. I mean, the IMU, I think the fastest it's useful to pull it at is around 100 hertz. If I really wanted to decrease latency between the IMU measurements and it getting out, then I could potentially use an interrupt coming back from the IMU to synchronize the polling. I don't know if I care that much, though. Got some of those headers that are really long on both sides. And now I feel like I probably need more of those than I actually have. There's a few more. Okay, I just need to clean up. There's some gross solder on these. Not clean enough to breadboard mount this. resistors. Let's get this back on the O scope. Power. Yeah, maybe that wasn't the problem. Yeah, so that's STL high and SDA is low. Oh, okay. If I take these off the host. If I reset it. Oh, resetting it helped. Am I going to need to bring the reset pin out? Like, let's try power cycling this again and see if it comes back by itself. It's off. Oh. Are we getting data? Is my keyboard in need of another reset? Whoa. I'm getting counts from the IMU, which means that my I2C transfers are succeeding. So maybe my I2C bus is working a little bit now, and now I just don't have the IMU actually in the right power state. Yeah, I mean, I2C peripherals, there are just so many ways to go wrong. So what's actually going on here? I wasn't expecting the bus to be this busy, I guess. I guess that's my tick rate. Huh. There's too much going on here. Let's simplify this little. If I comment out this, then I'll be sure to be only sending this first thing over and over and over again. That will simplify this a little. Let's try that. Let's keep that handy. So part of this is related to the way I decided to solve the kind of initialization problem. A lot of the I2C devices, or the example code at least, they just block the initialization until the device has gone through whatever initialization sequence they wanted. I don't like that for a lot of reasons. It means that a malfunctioning peripheral can block the entire startup. It means there isn't really any way to recover. So instead I have something where I try to do that asynchronously. And so I just made a little change to cause that to get stuck on the first step. It also looks like maybe my pull-up resistor is a little too high value. Maybe for 3.3 volts, I need something closer to 1K. Yeah, so as Robert's saying in chat, the shape on the wave looks wrong. Yeah, I think my pull-up resistor is wrong. I just wanted to simplify this because I think there are other things going wrong also. Yeah, so now it's stuck in this state where I guess that's SDA stuck low. So I think if it gets in this state, I mean, it's like, I don't know, that's a tangent. I mean, unstucking stuck I2C devices is like a whole other thing we could get into. Just not getting them stuck in the first place is maybe where I'd like to be first. Okay, so there it is, unstuck. No data coming through because we're still in the initialization phase. What was that? I think the serial port is getting unhappy. I don't know what's going on with the serial port there. I mean, it's possible this is a bug in my firmware. It's also possible there's just something going wrong with the debug interface, which is a problem I've had before. But yeah, rebooting it does not leave the IMU in a good state, so that's probably an issue. What are you even talking about, Robert? Seriously. just thinking about how to handle the reset case. I think I probably will just bring out another pin so that I can explicitly reset this. Otherwise, I think we're just going to have initialization problems. I also want to look at a schematic for this just to verify there aren't pull-ups. Oh. See, this is part of why it's so tedious having these conversations, because it's like, Robert says, does the Pi have modem manager, uninstall it or blacklist or USB support? And it's like, what the hell is that coming from? And then it's like, a while later, it's like, oh, AT commands. Well, I know where those are coming from. That's something Minicom does if you send it the right kinds of garbage characters. It doesn't have anything to do with modem manager. No, I'm not using modem manager. That's not what I was looking for. Those look like pull-ups. So maybe that, oh. Oh, level shifting. Am I just using this wrong? I don't want to use this on 5 volts. R6, 7, and 10. I mean, I could choose a different breakout board now that I got those in the mail today, but... Which other breakouts did I get? It's these. I don't really care about the AT command stuff in Minicom. Like, that was only happening because I already had a bunch of garbage going through the port, and that was the problem, was the garbage. I could make the garbage look nicer, but I'd rather just not have the garbage. What do we got here besides an amazing cat? This one. Oh. Robert's like, look over here, a red herring. Everyone look at the herring. Why do you use all the same? there's little. MP92060. This is a MPU9250, but I don't recognize that marking. Just looking for chip markings to actually verify that this is what we've got. Interesting. Usually the data sheets are pretty clear about how the chip is marked. An auxiliary I2C interface. One potential advantage here is I think there might already be library code for the sensor in the TI sensor lib. I just want to confirm actually what chip is on this board, because this labeling is kind of confusing. This seems like it'll be fine. But those chip markings, man. MP92. Oh, it looks like Robert found what we're looking for in section 10. P92. Ah, it's so tiny. Useful. Okay, well that confirms this is what we have. So this is an accelerometer and gyro, and I think this does not contain its own magnetometer, but has an interface for an external magnetometer. Is that right? Oh no, it does have a magnetometer. Great. I don't really think this will need the magnetometer so much, but... Alright, well maybe we'll switch out for this, because I don't think this is quite as nice of a sensor in some ways as the BNO 055, but it is certainly a popular and cheap and easy to get sensor, and it has, I think, all the features that we need, and there's already a driver for it, and the breakout doesn't try to do level shifting. So maybe that's more like what we want. So in that case, what is EDA and EC? Oh, that's the external. And ADO is what now? Okay, there's a pull down on there. Looks like pull-ups on the I2C. Regulator on VCC. And you can bypass the regulator. This is a nice little breakout. Alright, let's just put a header on this. Microhacks asks if that's one of the cheap eBay IMUs. That it is. It is a cheap eBay IMU. just thought of the headers the other way around. I think I kind of do. Because I think I'll want to kind of bolt this onto a mostly flat surface. This will make it a little easier to do so. Now I'm having second thoughts. Thinking mechanical design. Yeah, let's do it this way. Alright, ground, regulated GCC. I think yellow was clock and blue was data. Wow, that's much nicer. Let's get that on the scope. Yeah, that's what happens when you have your I2C bus not going through an unnecessary 5-volt conversion. It's still not the strongest pulse, but it's looking a little better at least. That is still the wrong code because we're trying to talk to the other sensor, so let's maybe swap it out for just using TI's library here. So for that, I'm gonna reset my keyboard again. Yeah, the Adafruit breakout board did a really good job of making it 5-volt compatible. That's just not really what I wanted for this. I think the other thing I was using it with was also 3.3 volts. So I don't know why it didn't cause a problem there. Anyway, let's see if this works. One thing I wanted to do is rename this file. This is no longer including a driver for that chip. It's just going to be a little more generic, maybe. Alright, so we'll want that, and pu6050.h. Okay, so still need all that same I2C initialization. So we have a init, we have an init callback. What actually happens in init? And why do we care about the callback? That does a device reset asynchronously, which seems fine. And I don't think I care about the callback. Just want to start out by calling this in init. Oh, the address is still a thing. Is there a default address in here? Default I2C address. That is 6.8 and 6.9. Assume it's 6.8 for now. And no callback. That'll do some stuff asynchronously. And then down here, I think there's just one command we can call to read everything. And then in its callback, we can kind of parse out the data however we want into a network packet. This function. This will happen at 250 hertz. Data and count. This is what I wanted. I didn't want this is like a low-level read. This is a higher-level read that stores the data in the structure. MPU6050 data read. And what data do we have? We could convert this into floats if we wanted, huh? It seems kind of convenient. This is really going to be 16-bit. I thought we had a magnetometer too, or is that only... I mean, it has an interface for an off-chip magnetometer, but there was also a section for magnetometer specs. So is this reading the magnetometer data? Looks like 14 registers starting with Excel out X. Hello, register map. Hello, register map. Is the register map in a different document? Okay, so we're starting the read here, and it gets 14 values. I mean, that's Excel and gyro. Where does the magnetometer even go? Maybe this is just confusingly written documentation, because this seems to be claiming that it has its own magnetometer, but then down here it looks like it's reading magnetometer data from an external sensor, and the register map over here doesn't have any room for magnetometer data, but it has external sensor data. Which is fine, like I don't really need a magnetometer for this. I'm just... I don't like having these inconsistencies in something that's so important. Oh! The 9150 is this, but with a built-in magnetometer. Okay. That might be a dead link. Well, there's a lot of things I could do. I think I'm going to assume that this chunk of data is what I want, and maybe instead of using this library's attempt to parse it out, I just want to read the entire thing into a buffer like I was doing before. Where does this even come from? External sensor data at 14. Really? Ah, 22 bytes. Yeah, let's just make a raw copy of this buffer and sort it all out on the host side. Looks like they rounded it up to 24. I don't know if that's because something else is a little bigger or because they just wanted it to be a multiple of 4, but I like multiples of 4 also. So in that case, let's do that. Let's see if that works. So I'm just using, this is like the laziest and simplest way of doing this. I'm just using their library to initialize the MQ6050, letting it grab all the data, including the optional magnetometer data. Just, I don't think this chip has one, but might as well leave room for it at least. And then we just copy that into the UDP packet buffer and increment our result counter. And, forgot a semicolon. Whoa. That's not what I wanted. That's just a bunch of I2C traffic going nowhere. Okay, so why is it getting in a loop? So much chat that I haven't had time to read. Yeah. Okay, let's comment this out for now and just watch the initialization sequence. So what would cause the initialization to get into a loop? If the address is wrong, maybe? Let's just try the other address while I read the documentation. Maybe that was the problem. Yeah, so it doesn't seem like it's getting stuck in a loop now. Let's just try turning this back on. Well, it's good to know it'll retry if the IMU isn't there. Oh, or maybe this is it not being there, and the other thing was it getting into a loop later on. That looks like it not being there. Did I just change that? I want to get this back into the state where it's getting stuck in initialization. Is that not it either? Is 6.8 or 6.9? Oh, what are we even talking about in the chat? It's like every time I look up there, there's something about choosing an address. Yes, I know there's a pin that chooses the address. I'm just trying to figure out what address it's on, and it's easier to just try both than to look at the circuit board. I don't know if I'm in the right mood to stream today. Let's just look at that code and see why it might be getting into a loop here. We decode this. Okay, 68, write, acknowledge. So 68 is the right address, then what does 6 mean? first thing we're expecting this to do is to reset the sensor. Yeah, power management 1. Ah, 6B. Great. Device reset. I wonder if I'm just calling it back before it's done. I mean, it's the one doing this though. Like this state machine. So, state idle. That. Is that another start condition and then a read from 1? How are we getting into this state? Oh, is this... Oh, okay, I got this logic wrong. This is the error case. So this is where we're going first. So that's the status read that we're seeing. That repeated address and the read. And then 01 is, I think, the register we're trying to read. And then we get a no acknowledge. So yeah, maybe we are just doing this too fast. But like, that's the way this driver was written. Power management 1. What is that? Yeah, I don't know where that 01 is coming from. So that 68 is our address again, but I'm expecting it to read back from that same register, that 6B power management register. Instead, we're getting a 1. Oh, maybe I need to hold off on sending anything else until I get the completed callback here. I mean, that wouldn't be the current problem though, because I'm not sending any other reads. So all I'm doing right now, setting up the I2C peripheral, issuing this init, which sends an asynchronous reset, and then starts the state machine polling for reset completion. And the rest of this isn't being used right now. I don't even know what that 01 would be coming from. Alright, so that's a start bit. So start bit 1, 0, 1, 6. Really, what was my... How is that 6, 8? Start condition. That, the acknowledge. So if that's the acknowledge, what's the write bit? And we have 0, 0, 0, 1. Forgetting where the relevant edges are. Okay, right, it's not supposed to change when SCL is high. That's what we're dealing with. So that means we have a 1, 1, 0, 1. Just confused about why we had that extra 1. Oh, 6, 1, 1, 0, not 1, 0, 1. Yeah, I know binary. Yeah, so that's the address. 1, 1, 0, 1, 0, 0, 0. Okay. Write bit, acknowledge, then the next byte. Am I forgetting a bit in there? Okay, we have 1, 0, 0, 0. That's the end of the address. This is the write. this should be the ACK, but this looks more like the ACK. That's 8 bits and an ACK. Yeah, I guess that's all right. And then we have 6B. Yeah. And then this is the one that's not acknowledged. So, I mean, all the I2C stuff looks fine. I just don't know why this is sending a read for 0, 1. Like, what does a read for 0, 1 even mean? Yeah, I don't know who's calling into there. It's almost acting like there's an initialization step I'm failing to do, and there's just garbage in some state somewhere. I mean, there aren't any commands, as far as I can tell, anywhere as low as 1. They're all kind of higher. So... So I'm assuming this is coming from a bug rather than something that's intentionally being sent out and then failing. And I assume that this is probably something I'm not doing right in how I'm using this module. So I think I should probably dig a little deeper into this and figure out where that 1 byte is actually coming from. Maybe just sprinkle in some UART debugging in this file, which is a little bit annoying because it's compiled as a library, so I'll probably have to pull this out and then make copy or modifications in my copy. But I think this is about all the on-stream debugging I have patience for right now. I should get a bite to eat and probably just continue debugging this stuff on my own. What was that saying? And so as I just finished, like Robert's giving me something to change, but like as I was saying, that I can't just change this and recompile. I have to change my build system or make a copy of this or something. So anyway, I'll keep debugging this. I just don't have the patience to do this on stream where people are bothering me about unrelated stuff all the time. So I think I'm just gonna code by myself because I like that. But I hope some of this was interesting. Juko seems to really like those mice. I just saw James's suggestion to route the I2C over twisted pair or coax. That seems completely unnecessary and not related to the problem I was having. Oh, and then Gionag is saying that I might just be using the wrong driver. That's totally possible. I'm just getting kind of frustrated because of all the noise right now, and I need some quiet before any of this is going to make sense to me or anyone else, I think. So maybe people at home are already further ahead, but I kind of need some peace and quiet to get this done. So I can sometimes stream writing code, but I think it depends on what state of mind I'm in right now, and right now this is just pissing me off. And that still doesn't explain why the driver I was using was sending out that one command. Anyway, until next time.